As you've probably noticed by this point, linear regression, especially multiple linear regression, is an extremely powerful tool for data analysis and root cause analysis. Unfortunately, the technique is also a bit finicky and complicated. It relies on a lot of assumptions, and you have to make sure those assumptions are satisfied in order to use the technique legitimately. What we're going to do in this lesson is take a very quick look at an alternative technology for root cause analysis based on the notion of classification trees. Classification tree construction is just a special type or subset of the field called data mining, using large amounts of data to somehow extract information. But you can think of this as being very similar to linear regression. To motivate this, let's consider a problem. Your firm wants to, say, patent a new technology, and the success rates for patenting new technology varies. Now, the outcome of a patent is categorical. Either you're successful or you're not successful. And really what you want to do is understand a conditional probability. What is the probability of getting a patent, or patent equals true, given some characteristics of your patent application? The problem is we don't know what these characteristics are. So really we have two tasks. One is to understand the root causes of patent success, the things that impact this conditional probability. And second, to actually make a decision, we want to maximize the probability, of course, of getting a patent. The starting point for our illustration of data mining technology is, not surprisingly, a data set. Now, the first thing I should say about this data set is that it's completely made up. It has really nothing to do with the success or failure of patenting. There's some other characteristics of this data set, however, which would make it extremely challenging for use with linear regression. First of all, a lot of the explanatory variables are categorical. Now, this isn't necessarily a problem in linear regression, but it does create a bit of work. The second thing is that the response variable is categorical, and we don't have the skills, at least with what we've seen with linear regression, to deal with a categorical yes, no, granted, not granted response variable. Finally, there's some potential interactions here, which you can deal with in regression, just we can't, we don't have the skills. Overall, this data set is fairly poorly behaved from a linear regression point of view, but you'll see that in classification tree construction, we have many fewer assumptions and many fewer restrictions on the data set. So what we're trying to do now is to use classification tree construction to identify which of these variables, if any, are relevant in explaining patent success, and which combinations of variables, especially the controllable ones, could we use to maximize the probability of patent success. The most important construct in a classification tree is this thing called a node. So here is a node that describes all of our training data. Now, training data is just our data set that we're using to learn the relationships. So in our training data, we have just over 1,600 patent applications. And of course, we also have the results of those patent applications. We know how they turned out. In this data set, approximately 466 to be precise, of these patent applications were successful. So just over 29% were successful, and roughly 71% were rejected. So those are our a priori estimates of success. What that means is if we didn't know anything about a patent application, we could go back to the entire data set, look at the historical average and say, on average, 71% of all applications are rejected. Now, what we're interested in doing is finding other variables or other things that somehow impact these probabilities so that we can do slightly better than these a priori estimates. The technique we use in classification tree construction is called recursive set partitioning, which sounds fancy, but it makes some sense. We start off with our initial data set, all 1600 records, and we find some variable that has some predictive power. And I'll talk about that in a second. But here we found the variable ownership, which describes the ownership location of the company filing the patent. So the ownership could be a United States corporation, a United States individual, a foreign individual, a foreign government, or whatever. So it turns out that if the ownership is a United States corporation, the probability that the patent is granted climbs from 29.1% to about 54.8%. Now this is just the historical data. There's 621 records that belong to U.S. corporations, and of those, 340 or 54.8% were successful. And so if it happens that ownership equals U.S. corporation, then our best estimate of successful patent is about 55%. If, on the other hand, the ownership equals U.S. individual, then in our data set we have, in fact, 100% rejected on a fairly large sample of 383 applications. Now, keep in mind that this data is completely made up, but it doesn't really matter. You can see how, depending on the value of ownership, we get very different probability estimates than in the root node. That is, our conditional probabilities based on ownership are different than our a priori probabilities. The question you might ask at this point is, why did we split the root node in the previous slide on the variable ownership? What's so special about the variable ownership compared to other variables, such as whether the company had a patent attorney? Well, there are many different ways to determine which variable is most related to an outcome of interest. And to illustrate this in a slightly more simplistic context, let's think about the test of independence that we saw previously. So imagine a situation in which I'm trying to predict a categorical variable called grade in this course, an A, a B, or a C, based on some other variable. And I'm considering two variables. One is the brand of sneakers students tend to wear, and the other is whether students have previous statistics experience. Now, I picked these two variables because obviously one is likely related to performance in the course, and the other is likely completely unrelated to performance in the course. And what we're looking for is an algorithmic technique that permits us to identify explanatory variables that have explanatory power versus explanatory variables that have no explanatory power. That is, they're completely independent of the phenomenon of interest. And if you recall, in probability theory, we have a result that holds when two variables are independent. If the two variables are independent, then their joint probability, that is the probability of A and B, is simply the probability of A multiplied by the probability of B. So let's see how we might determine whether preferred brand of shoes is independent of grade in course. So we start off with the assumption that the two are independent, and we calculate this joint probability as probability grade equals A times probability shoe equals Reebok in this example. So we can work this out, and we can calculate, under the assumption of independence, an expected number of A's with Reeboks as about 2.16. However, the actual number of observed students with Reeboks is 2. Now, you might say that's close or it's not close, but it turns out that it's pretty close. And if we do this for every cell in the matrix, recall that we can calculate what's called a chi-squared statistic, which is just a measure of how far off we are from our expectations given the assumption of independence. And we'll find out that this chi-squared value is relatively small. That is, the observed frequencies match up pretty closely to what we would expect the frequencies would be if preferred brand of shoes and grade in course were independent. In other words, preferred brand of shoes tells us almost nothing about the future grade in the course. If, on the other hand, we do the exact same arithmetic with experience in statistics, we see that in that first cell, our observed number of students with an A who have low experience in statistics is not 2.16, but quite different. It's 0. And in fact, if we go through every cell in this contingency table, we'll get a chi-squared statistic which is quite large. And a large chi-squared statistic suggests that our assumption of independence is not warranted. In other words, experience with statistics and grade in the course is not independent. They're related in some way. So right there we have the basic idea for a splitting heuristic in a data mining algorithm. That is, we can take the root node and we would prefer to split it on experience with statistics rather than preferred brand of shoes. And if we did that, we'd find that people with high experience with statistics would have a much higher proportion of A's. That is, we could better classify people with lots of experience in statistics. KNIME is an open source data mining product. It comes out of a university in Germany, and it's fairly similar to other products. Most notably, SAS has a data mining tool called Enterprise Miner, and although it's much more powerful than KNIME, KNIME is simpler and has many of the same features and in fact the same look and feel. So if you look at KNIME, when it starts up, you get a whole bunch of windows. I've shut them down, these extra windows, to get just two things. One on the left is the node repository, which has all the nodes. And this is very similar to SAS. So for example, there's some nodes for I/O or input/output. And then on the right, there's this big piece of graph paper, this workspace, where we're going to build a workflow. We're going to start by opening a data file. So I'm going to go to input/output or I/O and select the file reader and then just drag it on to the workspace. Now, every icon in KNIME has a little stoplight at the bottom. It's red when you start, and then after you configure it, it becomes amber, and then when you execute it and it executes OK, it becomes green. So I'm just going to right-click this icon to configure it, and I'm going to select a comma-separated value file that has all that patent data in it. So I click OK, and you'll see the node is now amber, the stoplight's now amber, and I can right-click again to execute, and it runs. Now, once I have my data read in, I might want to take a look at it. So I can go down to Data Views, and there's a whole bunch of different types of graphics. So for example, I might want to take a histogram and drop it onto the workspace. Now in KNIME, you actually have to make the data connection here. So what this means is the data is going from the file reader into the histogram tool. If I right click this, I can hit configure, and I have to tell it, well, which variable do I want to see a histogram for? In my case, I want to see the outcome of the patent. Now, relatively annoyingly, it has this aggregation information here. Don't worry about that now. Just delete it if it's there. Basically, what I want here is a histogram of patent. Now, when I run this, I can execute and open the view. You'll see it's not very exciting because there's only two values. There's rejected and granted. In fact, if I want to, I can close that and bring up a pie chart. Same thing, connect it to the data source, which is my file, configure it to show patent, which it does by default in this case. So it's going to show the values of the patent variable, execute and open views, and I get a pie chart. Now the nice thing about a pie chart is that it gives your percentages. So what I want to do now is better understand what's driving whether or not an invention gets a patent or not. So I want to go to the data mining node, and because this is a research tool, there's a whole bunch of different data mining methodologies and tools. I want the one called, rather unfortunately, decision tree. We're going to call these classification trees because that's what they do. They classify outcomes. Decision trees, at least in the business school, typically mean something else. What I want is a decision tree learner. It's a tool that learns a decision tree based on data. And it's a bit more complicated, but the basics are still the same. You connect it to a data source, then you right-click it to configure. And it says, well, what do you want, what classification or what class column do you want to use for learning? What do you want to classify? And remember, what I want to do here is classify the patent, yes or no, granted or not granted. Now there's different quality measures. This is the so-called splitting heuristic that we talked about at the start of this lesson. You'll notice that it doesn't use chi-squared. That is, KNIME as an algorithm doesn't implement this chi-squared heuristic. It uses a slightly different heuristic called the Gini index. We're not going to worry about that at this point. All the Gini index does is it goes through the potential explanatory variables one by one and tries to find one that gives the purest nodes. And I'll explain what I mean by purest nodes later on. There's a whole bunch of defaults here. I'm just going to ignore these for now. So really, I didn't have to set anything to get this going. I click OK, then I right click and execute to open views. So what you'll see here is something very similar to what we saw earlier. It picked the ownership variable as the root node. And the reason it selected that is because it creates some relatively pure nodes. What I mean by a pure node is that in this case, where US equals individual, it gave perfect classification. It says if ownership equals this value, then 100% of the records in the data set that satisfy this value, this ownership value, belong to the rejected class. So it's perfect classification. These other classification, they're not bad. You'd say, okay, well, if ownership was foreign corporation, there's like a 77.5% chance of that being rejected. So it's slightly different from my a priori probability estimation. 71%, this means I have a slightly more certainty. I'm getting slightly more information. And the same over here with foreign government. I'm getting slightly more information relative to my a priori estimates, the entire data set. What's interesting, of course, over here on the US corporation side is that the balance shifts. In this node, I'm slightly more likely to be granted rather than not granted. Now you'll see as well, there's a little plus sign here, which means these 621 records have been split again using a different variable. So if I click on that, you see that if I scroll up, you can see US corporation, and then it's being split on the patent class. And again, the reason it's doing this is because it's trying to get purer nodes. So for example, if the patent class is a semiconductor device, all of a sudden my probability of being granted goes up to 74, almost 75%. And there's another plus sign. So I can go even deeper in the tree. Now it's asking me about the status of patent agent, whether or not I have a patent agent. Now, if it's a US corporation and it's a semiconductor device and a patent agent is involved, then what this tree is telling me, it's predicting that the probability of success is almost 95%. Now, at this point, I should be a little skeptical because this estimation, this probability estimation, is only based on 58 records in the data set. And as we go deeper in the tree and we partition the data, pretty soon we get down to some very small amounts of data. So that's where we might want to go back and configure this and use what's called pruning, or specify a minimum number of records or data points, if you like, in order to draw a conclusion. Or I can simply move up the tree until I get a node that I'm comfortable with. I might stop here, for example, because I have 95 data points and I think that's acceptable. One problem with classification trees relative to regression is I don't get a really good measure of how good the model is. So for example, if I right click here and I go view decision tree, I don't have something like R-squared that tells me whether this is a good model or a bad model. So what I can do is create what's called a holdback sample and test to see how accurate the model is. So what I'm going to do is I'm going to leave everything the way it is, just move some things around, and I'm going to bring in another decision tree learner and what's called a decision tree predictor. Okay, so what I want to do is use this decision tree learner as an input to the predictor. And what else I want is two streams of data. So what I'm going to do is close this down here, go up to data manipulation, and what I want to do is split my data by rows. So if I look around long enough, I'll find a node called partitioning. So I'm just going to drop that in there. And you see partitioning has one input and two outputs, which makes sense. What it does is it splits the data into two sets, an upper branch, if you like, and a lower branch. So I'm going to configure this, and what I'm going to do is say, I'm going to click on relative here, and what I want is, say, 60% of my data to go to the top node, which means by default 40% is going to go to the bottom node. So I'm going to take my data and I'm going to split it, and I'm going to split it randomly. So it's going to randomly select, one patent application will go to the top node, a different one will go to the bottom node. So now I have a set of data I can use to learn a model, and I'll connect it there. And I have a set of data that I'm holding back, and I can use it to test how good my model is. So I'm just going to make sure that this one here is configured correctly. It's measuring patent. I'm going to turn pruning on right now see if that gets rid of some of the really small nodes with only 2 or 3 records. Maybe I'll say you need 30 records to split to a new level. I can play with that, no problem. And then here under predictor, there's really nothing to configure. It knows what's going on. It says take the node or take the model provided by the learner that's created using 60% of the data, and then bring it in here, and what it's going to do is says, okay, the model predicted this outcome, but along this path for that other 40% of the data, I know the outcome, so I can then compare them and say, is it right? So the last thing I need here then under mining, and you do get used to these this layout after a while, is I want to drop in a scoring node. And a scoring node is just going to say, how well did you do? So I right click configure, and I want to compare the actual value of patent to the predicted value of patent from the model. So that looks okay. What I can do now is execute and open this, and I'll run that entire branch and make this a little bigger. You can see that what actually happened is here in the column, and what the decision tree predicted is up here along the top. So I predicted granted and actually observed granted 129 times, whereas I predicted granted and saw rejected 59 times. And the opposite on the other side. So my tree, I predicted rejected 52 times when it was actually granted, and I predicted rejected and it actually was granted 401 times. So my overall accuracy of this model is about 82-83%. That's the overall accuracy with all the leaves in. That's not too bad given that given where I started. What I mean by given where I started is if you go back to your tree, if I just predicted rejected for any patent, if I didn't know anything about it, whether it had a patent agent or where it was coming from, if I just said rejected, I would be right 70% of the time. So that 83% accuracy has to be compared to your a priori. That has to be seen as kind of an information gain or a lift.